mikrofonu.
Okay. No. Tak. Dobre. Hello guys watching us at the stream. We are starting in 1 minute or so. Sorry for the delay. We again have to catch up. Yesterday it was half an hour. Today is just quarter an hour, but I have the bad feeling that it will fall into half an hour as well. Because there has been a small program change that after the modeling session, there will be a short break before the awarding ceremony. So there will be something like 10-15 minutes. And please remember, you got your voting sheets inside of the small booklet. We will collect them after the last session, after modeling. So make sure to vote, up to 3 votes per sheet for the best presentation award. And if you didn't vote for the best poster, during the next break, there are exhibited here inside, and you have these little green dots in your badges, so make sure to stick them on one of the posters so that we can decide on the best poster award. Thank you very much. Okay, Lukáš is steering the first session, so let's start.
Okay, hello everyone. Today here again on the terrace because we have nice weather. Well, a few skies over us, but I think it's much better than staying inside and get to sleep again. Well, the previous day in the night, mostly you had some deep conversations, and right now we are going for the next session, which is quite funny, deep learning. And in the past few days, it got a lot of attention. It seems a very important technology, and I think this is the first time it has its own session on CESCG. So let me not prolong this much further and ask the first author to present his paper, who is Bořek Reich from Brno University of Technology. And the stage is yours.
Thank you. Hello. Great, thank you. Okay, hello. My name is Bořek Reich, and I'm from Brno University of Technology. And today I'm going to talk about the exploitation of neural networks for fusion of camera and millimeter wave radar data. First question you might ask is that why we should help camera in computer vision applications. It is widely used, cheap sensor that produces high semantics. So what is the reason? The reason is that the camera where wonderful sensor can be negatively influenced by the environment, such as rain, mist, or mist, poor lighting conditions, and all. Millimeter wave radar is not, which means that we can benefit from combining these two sensors, and we can achieve more reliable system for computer vision. Another reason can be that the radar data are great for distance and velocity estimation, and we can use them for regional proposals as well. In the slide you can see frame from camera and the corresponding radar frame. This is one of the possible radar data representations. The typical one is point cloud, which you can see here on the left, where each of the cars is represented only by a few points, which means that this can be a disadvantage for this kind of representation. This is due to the process behind generating of these points, this point cloud, where we search in the radar signals local maxima, so we lose information. We can, however, use another kind of representation, as you can see on the right, where you can see a heat map that represents angle range radar signal representation, where all the values, or most of the values, is preserved in this representation of radar data. Well, so how to use the data I just described for some computer vision system? There are two main categories to which we can categorize the systems for using millimeter wave radar data and camera data. One of them is sensor fusion. That means that we use camera data and radar data both for training and when the system is deployed. On the other hand, we have camera as machine learning feature, which means that we use camera data only for training, and when the system is deployed, it uses only only radar data. This can be useful in situations where camera is not allowed for GDPR reasons, for example, and we can deploy the system in these situations. Here is an example of output of system that is the sensor fusion kind, and you can see outputs of the system from initial experiments, which were aimed towards the people detection and distance estimation. The green dot in the examples represent the point from where the distance of the object is calculated, estimated from, and I did not mention that in this example we used point clouds as radar representation. This experiment was conducted only on single frames, which means that no synchronization was needed here, and this is not a good idea in real-world applications, for example for traffic monitoring or self-driven cars, where we have objects with that are fast, with high speeds, so every synchronization error between these two sensors can be significant. That's why I'm now going to talk about sensor synchronization. Here is example of a system that uses embedded camera for synchronization of millimeter wave radar data and camera data. The main principle is here that the millimeter wave radar sends pulses to the embedded camera, and by sending these pulses it can control the shutter of the camera. So it means that when millimeter wave radar starts to collect data for next frame, it can send a signal so the camera can start the exposure. we can then take these two frames as corresponding and use them in our systems. This approach is really accurate. However, the embedded cameras can be expensive, as you can see in the table, and these prices are without lenses, so they are quite expensive. How can we replace this problematic part of the synchronization system? We can use another type of camera. For example, IP cameras, camera recorders, cameras. You can see examples of these cameras with their corresponding prices, and the main reason I'm showing it here is that these products are more affordable. And we can, however, we think that we can use them in our proposed synchronization system. We can use them for synchronization by using the audio input of these cameras. We can connect the millimeter wave radar to the input of the camera, similarly that we did in the embedded camera case, but in this particular case we use the pulses as an audio signal that is transmitted to the camera through some audio interface. We can then use these pulses as timestamps for the radar frames corresponding to the video of the camera. Here is a slide that should help you understand what I'm talking here about. On the left, you can see the audio channel of the camera, and on the right, the video channel of the camera. The pulses in the audio channel represent, each of the pulses represent one of the radar frames. That means that when we stop it, we can then take this camera frame and associate it with a radar pulse. This pulse can be then used to find correct radar frame. So we can, by this procedure, find the correct radar frame for given camera frame. This approach can be slightly modified, used also for, as you can see on the right, for multiple camera synchronization, where we replace the wave radar with pulse generator that sends audio signals to multiple cameras, and in this way we can then find corresponding frames in more video channels of cameras. The problem with this approach is that we assume that the synchronization inside of the camera, of the audio channel and the video channel, is well synchronized. It works, but it can not be the case. So we designed this simple circuit for the verification of whether the video and audio channel of the camera is synchronized. Here you can see some low-level PC Arduino, for example, we used, and that is connected to LED and to the camera through audio interface. We can then generate audio pulses at the same time as we change the state of the LED, and with this circuit we can then get results like this. These are the snapshots from a video editor where you can see audio channel and video channel of the camera. Video channels on the top and audio channels. You can see the pulse in the audio channel that corresponds to a radar frame. To estimate the shift of the camera channels, we need to compare timestamps of the frame start where the LED state has changed. So you can see in this case, I can't use the pointer, the LED state is changed. So we can then compare the timestamp of this camera video frame with the timestamp of the pulse in the audio channel. Here in the test measurement ID5, it was 24 milliseconds, and in the test measurement 98 it was 10 milliseconds. Why is that? The circuit is independent on the camera recording, which means that the pulse can appear anywhere between two camera frame starts. This is due to low FPS of the camera. So we can estimate from one camera recording the shift between the channels of the camera only with precision of 40 milliseconds. By recording more videos, we can, however, estimate this shift better. We can just find the lowest value, which is the 10 milliseconds, as you can see in the table, and we can take that as the shift of the camera channels. And we can then use this information for better synchronization with our proposed synchronization method. To estimate this shift between channels even better, we can use more LEDs, as you can see in the example, where we can run a counter of some sort, for example a gray code counter, and we can set a step of these counters for like 1 milliseconds, 3 milliseconds, and we can then estimate all the information we want only from one recording with better precision. Thank you for your attention. If you have any questions, please ask.
All right, thank you. I think you can have the microphone because you're answering the questions. All right, so that was the talk, and do we have any questions in the audience? We have about 5 minutes, so maybe even more. Time to wake up. All right, maybe even not for now. There's a question?
Well, the title says that it's like exploitation of neural networks for the fusion of camera and millimeter wave radio, and I didn't quite get where the neural network comes from in your session.
Yeah, the neural network is used for the detection and recognition purposes from the radar data and camera data. I did not talk about that too much. I focused on our work about the synchronization of the sensors that is essential for the fusion with the neural network that can be then used for detection and recognition purposes.
Thank you.
Yeah, I have a
Please.
question. I'm sorry, I have missed the beginning of the presentation, so maybe it will be like not a very good question. But like I have seen the keynote talk of Andrej Karpathy, who is like the head of the Tesla autopilot, and he said that they are not using the LiDAR and these kind of sensors anymore because like vision is enough and cameras are enough. So what do you think about this?
Yeah, LiDAR has this advantage that its performance is also limited by the conditions around it. So the mist or the rain or some other weather conditions, for example, can influence it negatively. However, millimeter wave radar is a different kind of sensor, which means that its properties are that it is not influenced by these conditions, so it can help camera vision applications for more reliable systems in these cases.
So was your work mainly on the synchronization or also on this part here, or is this just some other work and your work was really the synchronization, as it seemed when I saw?
Yeah, I mainly discussed the synchronization part, but for my master's thesis I'm working on the whole system for traffic monitoring that uses this synchronization for, here are, I don't know if you can see that, but here are real examples of system outputs from my system that we use for traffic monitoring, and yeah, that's it. I'm not quite sure if I answered the question correctly. Well, my master thesis is the whole system, but here I talked about mainly the synchronization method because it was described in the paper, but the work is almost complete at this point, but I did not want to talk about something that was not in the paper.
Yeah, maybe the title might then be slightly misleading.
Yeah.
Okay, do we have, okay, thank you for the question and also for the answer. Do we have any other questions now? If not, maybe I have one question. Maybe for the part of your synchronization. I'm sure you told us about the synchronization, but I'm not sure if you mentioned how many cameras can you synchronize, how is the latency, and well, maybe if there are some misses between the synchronization, and how can you cope with that?
Yeah, the synchronization method is dependent on the type of camera that you use, which means that it's dependent on that. The latency depends on the audio to channel shift, audio to video channel shift. So if it's big, for example, 50 milliseconds, then you have latency of 50 milliseconds because you have to wait for the one channel before it receives the correct information. When the LED state changed in the example on the slide, it was too late for the radar frame to appear. It appeared earlier, which means that we need to wait for the video channel of the camera for that mentioned 50 milliseconds before we can process it and find the corresponding radar to camera frames.
Okay, thank you very much.
Thank you.
And if you don't have any other questions, also I thank the author for the presentation.
Thank you.
And we can go further. And our next participant and also the presenter, his name is Maroš Kollár, and he's from Slovak University of Technology with his topic Multiclass texture synthesis using generative adversarial networks. There you go.
Hello, my name is Maroš Kollár, and today I would like to present you my work on multi-class texture synthesis using generative adversarial networks, where I focus on synthesis of multiple types of textures by one trained model. The motivation behind texture synthesis is pretty clear. We synthesize data if the traditional data acquisition is resource consuming. But why would we want to synthesize multiple types of whatever by one model? The main motivation behind this is to save storage, because deep learning models could be very large, and this also brings us an opportunity to create transitions between different types of texture that is hard to acquire by separate models. There are multiple ways how to divide textures into groups. For our work, we mainly focused on non-stationary homogeneous textures, that are textures that don't have any regular pattern, but are mainly created from one type of primary texture. The current state of the art in synthesis is provided by generative adversarial networks. The training of this network is provided by competition between two types of two types of networks. Generator, who creates content and wants to fool discriminator, and discriminator, who tries to find out if the input is real or synthesized, and of course doesn't want to be fooled. By their competition, they are both improving their skills. That leads to better synthesis. In field method of multiclass texture synthesis, one of the related solutions is proposed by Lee and others. The interesting part of this solution is a two-stream generator, which one stream provides the synthesis of the output, and the second stream provides information to the first stream about what type of texture should be synthesized. One of the input for this network is information about what texture should be synthesized, created as one-hot encoding vector. Another solution is proposed by Bergman and others. They focus mainly on periodic textures, and one of the part of the input, they name it global part, decide what type of texture should be synthesized. The problem with this solution is that the global part is sampled randomly, and we cannot decide what texture should be synthesized if we don't know what we are looking for. This disadvantage was improved by Alano and others, who changed the global part from random noise to output of encoder that was learned during the training of generator and discriminator. The input of encoder was example image or example texture. So let's move to our solution. Because of multiple parts of our solution, we will take it step by step, starting with generator. As you can see from the two-stream architecture, we use the generator proposed by Lee and others, but this generator for the task of non-stationary texture wasn't enough, so we improved it by implementing it as progressively growing. Progressive growing GAN, or architecture of progressive growing, means that at the start of the training we only train a few layers of the network that produce low resolution images, and then during the training we add more layers and improve the resolution, quality, details, and so on. We also made some minor changes, like changes in number of filters, and changed badge norm to instance norm based on our experiments. Discriminator, we use discriminator proposed from DC GAN paper. We also, to deal with problems of quality of output and synthesis of multiple type of textures, we combined Wasserstein loss function with style loss function, and also improved discriminator by information from mini-batch discrimination that deals with mode collapse. Mode collapse is one of the problems when the generator creates the same output over again, no matter what we have on input. So mini-batch discrimination basically tell how similar there are samples in the batch. Okay. Because our solution wasn't just about the synthesis of multiple types of textures randomly, the important part of our solution was the input for generator. We have multiple variants. Variant A input consisted of 3 parts. The selection part, that is one-hot encoding, say, as the solution of Lee and others, that tells out exactly what type of texture should be synthesized. Then there is a random noise that creates the variability between the samples. And we also added texture part that is obtained by example texture by pre-trained classification network and its features, and also the principal component analysis algorithm. We used 2 different types of information that tells us what texture should be synthesized, because we wanted the exact information about texture class that is provided by selection part, and also some we wanted to control what type of internal variability should be synthesized, because, for example, if we want to synthesize bark of tree, there are multiple types of bark, and in our work, bark is just a bark, and there are internal variation of it. As you can see, the results of this variation was, I hope I can say, pretty good. We could decide about internal variation, as we can see, for example, on bark. But there are still some problems with texture, for example, of roof tiles that are stationary, and the whole dataset was non-stationary, just this one class was stationary. And also the problem is with a class of pile of rocks, where there was too much of internal variation, because we have small rocks, big one, and different colors, and so on. We evaluated this solution on a survey where we proposed randomly selected synthesized and real textures to the participants. Based on the results, the difference between correctly answered surveys for real texture and synthesized was extremely significant. So we can say that our textures were able to fool a human discriminator. This solution had good results, but the controllability, manual controllability, was really hard because of multiple options of selection part, texture part, and so on. And also, if we wanted to create some transition between different types of textures, we need to find the exact point for texture part and also selection part. So it wasn't really intuitive and easy. Because of this, we proposed variant B of our input. We get rid of the selection part and change the texture part from obtaining by classification network to pre-trained Siamese network. The intuition behind changing the pre-trained network was that the Siamese network was trained to distinguish between the similarity of the same class and the different classes. So the inputs of the same class should be closer to each other than the other classes. As we can see on the visualization of texture part and its clusters that represents different types of textures, they are more separable than when we used the variation A. Also, manual control was by this variation much easier, because we changed texture by just texture part and moving point in the 3D space. And this also brings a much easier controllability and the transition between different textures, as we can see on the images. But there was one problem, that the comparison of variation A and variation B during the similar training was that the variation B had lower performance or lower results. So to conclude our work, we propose another solution of multiclass texture synthesis with controllability of the classes and the intra-class variations. And we also have some things we can do in the future work. For example, one of the ideas is to improve Siamese network by training it on strong and weak similarity between the texture classes by its similarity. That's all from me. Thank you for your attention.
All right, thank you, Maroš. And now we have quite a few time for the questions. So, anyone here who is interested maybe in textures or generative networks?
Okay, can you synthesize texture tiles that are tileable?
Currently, this is just the proof of concept, so they are not tileable, and that's maybe the next step for the proper usage of this solution.
Have you thought about like time-dependent textures, like in videos and stuff like that?
No, that wasn't the idea, but well, I think if by the controllability of intra-class variation, we could create the different variations and then like interpolate between them and so on.
So in the beginning you mentioned potential use for some sort of like augmenting the like training data for medical images. So what kind of like textures would it be like? Is it something completely different from the experiments you have done? Or is it something that the network could already do?
Well, in my solution, we just changed the data and we could synthesize, for example, medical data. But one of the colleagues on the university is doing a research on, well, synthesizing variations of histology images that would be used for the training of segmentation networks and so on.
Because like I'm interested in how you actually get like what is texture from the what is like content and what is texture from like the medical image. And how would you get the actual training data for this? That could be tricky, I guess.
Well,
Could be, but I think some microscopic data or
yeah.
some others.
For example, histology data are colored by some colors with, well, the cells and so on. So basically, it's a texture in some sort of way.
I want to ask about visualization of the multiclass variation. I didn't get like what are the dimensions? It's like three highest eigenvectors from the PCA space.
In the variation A, it's a 5D space. This was obtained by experiments where we started with 3D dimension, but it wasn't enough, so we switched to 5 dimensions. And the intra-class variation is that we know where we should find what class of texture. For example, if we want slabs, we go to the area where is the blue cluster, and then we just move in this space, and that creates. We still get the slab, but if we move the values, we get another, well, different slab.
Yeah, I know, but what are the dimensions? I can see here that there are three, like the dominant dimensions from PCA. But what about variant B? Like, what are the dimensions there?
In variant B, it is the 3-dimensional space. Does that answer your question, or?
From PCA.
No. For the variation B, we used just the Siamese network
Okay, so first three.
as output. Yes.
So sorry, just maybe to specify the answer, the 3 you mean is the output of the Siamese network, or you just transferred the output of Siamese network to some other features?
It's just the output and scaled by min-max scaling.
Okay, so I think that might have been the last question. And thank you, Maroš, for your presentation, and I think we can. And we can go for the third presenter that is still with us, and it would be Balázs Szőke from Budapest University of Technology and Economics. And his work is about analyzing architectural floor plans using neural networks.
I would just check the next one. Just a second.
And just a technical pause for a while. Because we are now in a hybrid mode, and the last presenter is not here with us, and probably, hopefully, he will join us remotely. And now we are just checking if he's able to do it.
Uvidíme, čo. Nie. Zrejme to nehalo celé. Dobre. Okay, go on.
And we're back. So here you go, and stage is yours.
Hello everyone, thank you for the introduction. My name is Balázs Szőke, and I will indeed talk about analyzing the architecture of floor plans using neural networks. In the 21st century, architectural design workflow has shifted almost exclusively to computer-aided design because it's easier, cheaper, and faster to handle digital media than traditional pencil and paper techniques. CAD software also offers numerous possibilities to automate very time-consuming processes like creating section views or visualizations of the building. So what's the problem? There are cases where the CAD file is not available for a building or for a floor plan. Think about, for example, working with archive documents where the floor plan is only drawn by hand on a piece of paper. So our idea was about solving this problem and offer opportunity to get access to the benefits of having a CAD file in these cases. So we wanted to create a system that is capable of converting an input to the image of the floor plan into a parametric representation that later can be used to generate a proper CAD model or a visualization of the building. To be more specific, we want to achieve this kind of system where the input is a 2D image of the floor plan. We have the parametric description as the output, and we create a 3D visualization to present the strength of having a parametric description. Our plan to solve this task is the following. We used neural networks with a differentiable rendering based learning method. What is differentiable rendering and why we want to use it? You can see our system again in the gray dotted rectangle. There is the input, it goes into a neural network, and the output is a parametric description of the image. In a more traditional supervised way, we need a data set where each input is labeled with the information about how our output should look like. And creating a data set like this from real floor plans, architectural floor plans, is very expensive and a challenging task to do. So we choose to take a different path. And since the main goal for the neural network is to produce parameters that represents an image which is very, very similar to the original input image, the best metric for the performance of the network is the visual similarity between the input image and the image that the parameters represent. So we can achieve that if we render this image from the parametric description. So that's what we do. We create a renderer that renders the parametric renders the output image from the parametric description, and we compare these two images to train the networks. This rendering step must be differentiable in order to allow backpropagation from the last function through the entire system. Let's take a look at the main steps of our system. First, we need to do some preprocessing on the inputs. Then we can obtain the parameters from the image. And finally, after post-processing of the parameters, we can reconstruct the floor plan. The first step is about cleaning the input. we focused on parameterizing the walls of the floor plan. So we want to, on the upper left corner you can see the original floor plan. We want to clean this floor plan to have an input where only the walls are visible and the other distracting labels and other symbols are erased. We used mathematical morphological operators to separate these symbols by line thickness. Here is the results of this. So we get 3 pictures, one with only the thick lines, one with the medium thick lines, and one with the thin lines. We can do that with this simple trick because in architectural floor plans, line thickness has semantic mating. It means, for example, walls are usually drawn with thick black lines, so with this simple trick we can easily separate those. At this point, we can also find the locations of relevant objects on the floor plan. We use the heuristic arc detecting method to find the locations of the doors. The next step is where the parameterization happens. We have this cleaned input where only the walls are visible. We split this input into equal sized little tiles in order to reduce the complexity of a single input. And then we feed each of these tiles into the neural network to get the parametric description of each tile. But what is exactly the parametric representation we want to achieve? We see a floor plan as a union of walls, and each wall as a rectangle, because walls usually have a uniform width and rectangular cuts on the ends. So rectangle is a very close approximation for wall in our eyes. And we can represent each wall or each rectangle with its start and end point, positions, and its width. So in summary, the output of the network will be a parameter matrix where each row represents a rectangle. So each row has the start and end point, position, coordinates, and the width. To achieve a network like this, we need to find the right network architecture, create a balanced data set. Obviously, we need to implement differentiable rendering for the training and choose a suitable training method. Our network architecture consists of 3 parts, main parts. There's an encoder network, which converts the input image into a feature vector, which will be then the input of the following 2 subnetworks. One of the subnetworks tries to guess how many rectangles or walls are on the picture, and the other subnetwork creates the parametric representations of these of the right number of rectangles. Earlier I mentioned it's very hard to create a data set from real world floor plans where we have the labels of what the actual parametric representation of the floor plan is, but because of the tiling step, we no longer have to obtain the parameters of the whole floor plan, only a small part of the floor plan, and the complexity of the inputs are heavily reduced, and thus we can implement a training data generating algorithm what generates very basic shapes and not so complex inputs, which will be then received by the network in real world use. And if we have a training data generating algorithm, then we can have a theoretically infinitely large data set, so we can avoid overfitting. one of the most important parts, obviously, is the differentiable rendering. Creating a differentiable renderer with such a limited functionality we need is not a complex task. Basically, we need a rectangle rasterizer algorithm, but instead of having each pixel 0 or 1 value, where the rectangle are and where it is not, we need to have each pixel continuous value between 0 and 1 as a function of distance from the closest edge of the rectangle to have gradients all over the image. Just a quick reminder how this differentiable rendering fits into the learning process. We put this differentiable renderer behind the output parameters, and then we have an image that is coded by the parametric representation, and then we can compare this image with the original input image, and thus we can have a very good metric about how our network performing. So training method obviously use this comparison as the main part of the loss function, but we use the hybrid training method and use this unsupervised learning technique, and because of the training data generation algorithm, we can access to the actual parameters of the input image, so we can use that in our loss function as well. It's not a trivial task to compare these parameters to the outputs of the network, so we cannot rely entirely on this supervised part. That's why it is so important to have the unsupervised part. One of the last steps is the post-processing part, where we can compensate small errors on the parameters, like the ones that introduced by the tiling step, to have a very nice consistent wall structure. Finally, we can reconstruct the floor plan from these parameters. You can see two 2D reconstructions on the top and one 3D visualization below. We wrote a little Blender script to generate from the parameters this little 3D scene. Obviously, there are numerous ways of improving the system. We can extend it to fully reconstruct the whole floor plan by recognizing other symbols than doors, like windows, furniture, and so on. And obviously the network architecture can be improved as well. For example, the logical next step would be to somehow integrate the concept of tiling into the working of the neural network. If you're curious about the details of the whole process, then check out our paper, and thank you for your attention.
Right, thank you. Well, do we have some questions now?
I have a question regarding the parameterization. So it seems that it's not necessarily unique for like a given image. Like, how do you determine the order in which you enumerate the different rectangles, right? Like, I would assume you could like predict them.
Yeah.
Is this like important, or is it not a problem?
Thank you. Actually, this is why it's very hard to use the actual. So that's why we need to use an unsupervised method to train the neural network, because yes, it's very hard to find a parameterization which is unique for an image, and you can change the orders of the rectangles in the parameterization, and if you render an image from this parameterization, it's not important the order. You will have the same image if you change the order, and then the rendered image from the parameters will be the same as the input. So that's way you can compare these images.
So, but have you considered like using a structure, like object detectors? They usually use some sort of structure at the end of the network, and the kind of the structure determines how the objects are represented. And some of them are not like unique in some sense that you can represent an object in multiple like echo boxes and so on. But there's like some other detectors that, like CenterNet, that they have like very specific point that is always represents the same thing, and it is unique. So have you considered like changing the representation so it is not just kind of permutable in a way, but that we would like be related to the spatial structure of the like on the output? But like it wouldn't be a problem in the method, I think, because I don't see like why that would not be like a good approach, but maybe.
Yeah, we can experiment with the parameterization, but there are other problems like you have multiple good parameterization for a rectangle itself, so you can flip the endpoints to have the same rectangle, so it's not very unique itself, a single rectangle. And why we choose this way, the parametric representation. So with this differentiable rendering trick, the whole system is a very lightweight way to do this task, and if we put other components to somehow make it easier to interpret the parameterization, it gets more bigger and bigger, and one of the most important thing that the parameterization, it should be readable by human eye. So we wanted to keep this as simple as possible, and this is a very organic way to represent walls. Like walls have start and end points, and every wall has a width. So that's why we decided to keep the parameters this simple. I don't know if I answered your question.
Yeah, I guess exactly.
Right, thank you. I have a pretty similar question, but at the end you mentioned that there are some features in the architecture like door windows and stuff like that that you need to work on. So my question is whether you have thought about extending the parameterization, like the model of the parameterization.
I think.
One more question.
Yeah.
Okay. Yeah, and the second one is in this context you actually explore the existing parametric representations like of the architectural plans, because there are like, I don't know, several like formats which you can get from the architectural software, and like most of them are proprietary, but some of them are like human readable, so you can basically like get what you just mentioned, like human readable parametric version of that.
Yeah, thank you. So the first question is, so I didn't want to include the other symbols into this parametric description, because in the preprocessing step, if you find the location of these symbols, like we did with that with the door symbols, you can have the information, the location, and also what the object is. So you don't have to. So you already know what objects did you find. So you put this in your bag, and you already know what objects did you find. And the hard part is to find objects that don't have features like walls, and we use the neural networks only for the walls, because other objects can be found in other ways. Yeah, and the other question is the goal is to produce a parametric representation that is like this. So the main goal is to achieve a proper CAD representation or a proper CAD format, which can be generated from this representation if we extend it with the components what a proper CAD file has, like door and furniture symbols or labels. So that will be the end goal of the process to actually implement everything into this into the system to have the representation of a proper CAD file. But this is a very simple representation, so it can be interpretable. It can be interpretable by humans very easily. I hope you agree.
Yes, thank you.
Okay. Well, thank you for the questions. I think we're now out of time. And now we are going a little remote. And next and the last participant from the fourth country, actually, because this section is with 4 presenters, each from the different country, and the last one is Eibensteiner from TU Graz, from Austria. And I'm not sure if we have him online or have him only pre-recorded.
Uh-huh. Is the right word.
Yeah, we are at now we have to find the aha.
Okay, this will be
It's PDF.
innovative. So
The fun part about this is that we have pre-recorded speaker, we have the PDF presentation, and now somehow we have to merge it together.
Aha, tak to sprawił. No dobra. Już to widzisz. Już to widzisz, jak to. Co to widzisz? Jak nie wiem, czy sobie to podali.
niech to. And someone has to switch the slides. Yes, I think the chair will do it. What is... Okay. We will try if it works like this, but no, actually not, because when you start switching slides, this window will go away.
You don't need to see.
I need to...
But the viewers from the YouTube might. It's all for the clicks.
Let's try differently, sorry.
Media player. Tento nemá Anisotropic. Velcečko, no.
Or you can put it on the notebook screen and turn the notebook.
For you, yes. For the YouTube viewers, maybe not. Okay, let's do it like that. I think that's, yeah. This means for YouTube we need to do like like this. So, is this okay for you, kind of?
Perfect.
Yeah, let's try. number 37, room number 15. We do. Perfect, thanks.
I'm from Arts University of Technology. This is my presentation of my paper, Weight Redistribution Algorithms for Sparse Neural Networks, that I wrote under supervision of Matthias Pager. I'm going to start with a quick introduction to the topic, continue with an overview over the algorithms that I compared, and finish with the results of my evaluation. Sparse networks in general are ones when not every neuron of one layer is connected to each neuron of the next layer. They are already used to speed up inference or reduce the memory requirements of neural networks, for example, in mobile applications or for VR headsets. The point of the algorithms I compared is to also reduce the training overhead of these networks. I used the PyTorch library for sparse neural networks developed by the team of Matthias Pager, where sparse forward and backward passes had already been implemented. My predecessor showed that training sparse neural networks with reduced usage of resources is possible in CUDA. So the goal of my work was to maximize the accuracy of the resulting network while keeping as much of the benefits of sparse training as possible. I will quickly go over some terms that are important for sparse training. Note that some of them might be used differently in other work, as there do not exist any well-established names yet. Most research until now focuses on the creation of sparse neural networks through pruning. That's the first picture. That means training a dense neural network until convergence, represented by the colored lines in the image. And then the connections are removed. In the most simple case, the smallest weights are removed, but there are also pruning algorithms that take into account other measurements. For example, first or second order gradient information. The second one, static sparse training, means starting out with a sparse neural network and only training the weights without changing any of the topology. It has been shown to lead to greatly inferior performance compared to pruning. And then the third one is the one which is important for this presentation, which is dynamic sparse training. It changes the topology of the network while training the weights, and this can lead to networks that are comparable to the ones obtained by pruning. So in general, the objective is to get to the performance that can be obtained by pruning, while also having the benefits of a reduced training overhead. In this slide, we can see the basic training schedule that actually nearly all of the dynamic sparse training algorithms follow. First, the topology and the weights are initialized randomly, and then the training cycle alternates between training the weights for some iterations and the redistribution step that you can see in the lower half of the picture. In this step, the topology is altered. Some of the connections there are removed and others are added. So the main difference between the algorithms is where this happens respectively, so where the connections are removed and where they are added. The amount is mostly determined by some hyperparameter that is tuned to get the best results. In total, I compared 6 different algorithms. 3 of them were only slightly adapted from their form in the original papers, mostly to be more comparable and also to be usable in the framework that I had. 2 of them were created from pruning algorithms, and only the criterion for removal of weights is the same as in the paper. We'll get to that later. The first one is the redistribution random algorithm. It is based on set, and it just removes the weights that are closest to 0 per layer, which is called magnitude-based removal. It adds the same amount of weights at random locations, and it already has a higher accuracy than a fixed topology would have. The second one is called redistribution gradient and based on RIG-L or rigging the lottery. It again features magnitude-based removal, but this time it adds by the highest magnitude gradient per layer. So already a little bit more sophisticated. It has been shown to outperform SED. Now we come to gradient global, which is also based on RIG-L, and it actually uses the same criteria, but it applies them globally. So it's possible to relocate one weight from one layer to another layer. It is still not necessary to hold the full gradient in memory, as it can be calculated, as the maximum can be calculated iteratively. This is important for the memory consumption of the algorithm. The next algorithm is called redistribution loss and was created by my predecessor, Alexander Ertl. It is an approximation to the gradient algorithm and only calculates the gradients of weights at the neurons with the top k losses. So it saves some resources in the process. Then we have the two algorithms Wood-Fisher and Wood-Taylor. They are both based on the Wood-Fisher pruning algorithm, and the problem they try to solve is that, especially in very deep neural networks, the magnitude of a weight might not be good approximation for its significance. So the significance of a weight is usually defined as the expected increase in loss when the weight is removed. It is also problematic to approximate this loss using the gradient, as the gradient of a fully converged neural network is close to zero, but that does not mean that its weights are not important. Now the intuition is to use a second-order approximation to solve this problem. More specifically, the idea is to minimize a quadratic approximation of the objective function, which would be one step of a Newton's method. But to this optimization problem, we add another constraint that our desired number of weights becomes zero, or in other words, are removed. To solve this directly, we would have to calculate the expected loss for every combination of weights that we can set to zero, so every combination of weights that are active. This would not be feasible, therefore we set the constraint to only remove one weight, and then we calculate that step. So we have a bunch of steps, each setting one weight of the layer to zero, and each increasing the loss a different amount. We then take multiple such steps, actually the ones where the loss increases the least, and add the weight updates together to get one weight removal step. To save additionally computational resources, we also use the Fisher information matrix instead of the hashing, hence the name. This holds under the assumption that the conditional model distribution is equal to the conditional distribution of the data. And we calculate this approximation only blockwise around the diagonal. Finally, the only difference between Wood-Fisher and Wood-Taylor is that for the first one, we assume the gradient to be zero, which is often done for pruning algorithms, because they are applied at the end of the training, where at least theoretically all partial derivatives should be close to zero. So in our case of dynamic sparse training, this assumption of course does not hold, but it simplifies the calculation and works pretty well in practice. Now we come to the experimental setup. I tested on two datasets. Higgs is a binary classification dataset of particles based on sensor data. K-MNIST is a character recognition dataset similar to the popular MNIST, but using an ancient Japanese font which makes it more challenging, and therefore it's less prone to overfitting. I used a simple MLP architecture with ReLU activation functions, and I trained them at 3 different densities. Additionally, I created 2 dense networks as baselines. One with the same architecture as the sparse neural network, from now on called neuron equivalent 1, and one with less neurons per layer, which has about the same number of parameters as the sparse network, at 10% density called parameter equivalent. The redistribution step of all algorithms occurs once every epoch and starts by redistributing 50% of the active weights, and this fraction is reduced over the course of the training run. And at 3/4 of the epochs, the redistribution stops entirely and only the weights are trained from then on. So the topology stays the same in the last quarter of the epochs. So the biggest challenge actually in training was to prevent the networks from overfitting, which actually is something that, in my opinion, happens in some papers that I read. That is problematic because in this case, the sparse network performs better because of their lower representational power. The sparsity of the networks reduces the memory overhead already at 10% density compared to the neuron equivalent dense network, even when the redistribution algorithms are already taken into account. The only exceptions are Wood-Fisher and Wood-Taylor, where a meaningful block size for the empirical Fisher matrix unfortunately increases the memory consumption drastically. Additionally, the current implementation of sparse forward and backward passes is slower than the neuron equivalent dense network by about 1/3. So this is due to the current state of the implementation in CUDA. The redistribution algorithm in general adds a significant slowdown, but between different algorithms, there is no big difference. So in summary, training is slower but uses less memory. Now we finally come to the accuracy of the resulting models. As expected, at 10% density, all are better than the dense network with the same amount of parameters. As can be seen, there are significant differences between algorithms. In general, it can be said that global algorithms, more specifically Gradient Global and Wood-Fisher, perform better. Interestingly, they adjust layer densities in a similar way and probably benefit most from this. On the Higgs dataset, we have a similar picture, but the performance deteriorates a lot with less parameters, or in other words, a lower density. Global algorithms again have a better performance across the board. Thus, we come to the conclusion that redistribution across layers yields better accuracy. Second-order approximations can improve this even more, but it is questionable if it pays off. Because of the introduced memory overhead, one might be better off training a dense network and using pruning. Still, for future development, it might be interesting. For example, if only a speedup introduced by the sparse training would matter and memory wouldn't matter as much. Generally, it will be interesting to see the algorithm's performance on larger networks and datasets. Thank you for your attention. I'm happy to answer any questions afterwards.
Okay, thanks to the presenter. I'm really not sure how he will answer the questions.
I know.
This is me first time holding a baby. Thank you.
I just called with Paul, and we arranged that he would send me a link, and we start a chat, a live chat with him. But it's not there yet, so the second option is to have a coffee break now, and to start with a Q&A for this paper in the next session. What do you think?
Wait 10 seconds.
Coffee? It looks like people are eager for coffee. Okay, I make one more check. If there's nothing, then we do it at a coffee break. There's nothing. So let's have the coffee break, and afterwards I hope we have the Q&A. If there are questions for that.
How long are we talking? 1 minute. 1 minute, yes.
10 minutes?
It's a short one because we are having the KV. This is part of the KV, the next session.
Okay, 10:30, so we'll start at 10:30.
Okay.
Sure. Prepáč, Mišku, to baví. Come with me. Stano, dievčatá ti pomôžu. Poďte na to šup.
Unfortunately, I left my program at the dinner yesterday. Are these additional programs?
So, welcome to another History KV. This time I do the introduction instead of Michi, because Michi is somewhere back there at a coffee break. We have a little delay in the program, so the coffee break is still running. We will start the next, and that is already the last session soon of CESCG. What awaits us today are 3 more presentations on the topic of modeling. The first one is a poster presentation, so it's shorter. It will be on an Anisotropic Reflectance model for predictive rendering of FD and 3D printouts. Then there will be 2 more paper presentations by students here at the CESCG. That would be Depner from TUV, who will speak about improved integration of depth images in 3D models. And then Čavarga from Comenius University having an interesting talk on Advection-Driven shrink walking of triangulated surfaces. Stay tuned. The coffee break will be finished soon. For those of you who didn't come, I hope you come next year. This year we have great weather. Yesterday it was sunny and hot. Today it's cloudy but still very nice. We are outside. We are not in a conference hall. So it's very pleasant and we feel like in the middle of nature, because here all around us are the tops of the trees, because we are out at the terrace on the first floor. Maybe I can just quickly give you an overview. I rotate the camera a bit, like this. So I hope you join us the next year, end of April, and we will start in 1 or 2 minutes.
Ich bin, glaube ich, danach dann dran.
Okay, also wir sind zurück und hiermit startet das KV. Sorry, I was speaking German, I don't know why. We are starting now as part of the seminar at TUV, the KV, and actually this session starts with a Q&A of the last paper from the previous session, because that was our hybrid talk, and we managed to connect. So Paul Eibensteiner from TU Graz is now live. I will switch here for the live stream as well, that you can see him. Actually, just this. And we can have the Q&A now. So I will also change the microphone here a little bit that I catch the questions. And yes, let's start with the Q&A for his paper on optimizing weights for deep learning. There were some questions, right?
Yeah, maybe you can summarize in 2 or 3 sentences again the paper, because we had some problems following the slides correctly and the slide transitions here on this side. So maybe the main point or the main contributions.
I'm sorry that was a hard part. Thank you first of all for being able to do this virtually. So summarize the paper again in 1 or 2 sentences. Well, basically, the idea is that I developed algorithms to train sparse neural networks, or I compared some that already existed, and I created 2 new ones. And well, I think I don't know how many people of you are generally know the idea of sparse neural networks, but it is generally a network that is not fully connected. So 2 layers of not each weight of one layer is connected to every weight of the next layer, but there are some connections basically missing. And I used a framework that already existed that was programmed in CUDA to test the different training algorithms for how good the resulting network were. So how high is the resulting network accuracy, and how much resources does the training algorithm need?
Okay.
Yeah, I guess that what is the idea behind the version that you developed, your new version? What did it add? What was the idea?
So the basic idea was reusing an idea that I read about in a paper that was used for pruning algorithms. So pruning algorithms are a neural network that is fully trained, and then remove some connections to get to a sparse one that you then can use for inference. So in the application of a fully trained network that doesn't change anymore, for example, in some mobile deployment later. So I used the basic idea from this pruning algorithm, and the basic idea from this pruning algorithm is that you take a basically a second order derivative. So you make a Newton step, but you have an additional constraint that some of the weights are set to 0. That's the basic idea. So you and you want that the resulting loss when you do the step where some weights are set to 0 should be as small as possible, of course. So the increase in the best case, of course, the loss even decreases, but the assumption is that because you're removing some of the weights, so you're setting them to 0, you will have an increase in loss, but you will try to minimize this increase in loss. And then there are some optimizations on top of that, that I can go into detail about, but that's like the basic idea. You do a Newton step, you set some of the weights to 0, and that's how my algorithm removed weights. And then the step when you add other weights, so you try to relocate them, so you have to first remove some and then add others. And while adding weights, I used another idea from another algorithm where you just add the weights with the highest gradient. So you calculate the gradient for all non-active weights, basically, and you sort them by their magnitude, by the absolute value. And then you take the biggest ones because you assume that these are the ones that are going to change the most in the next training iterations, and therefore have the biggest effect on the output of the network, so on the accuracy. You're welcome.
Andre, question?
In your paper, you mentioned some intuition behind each alternative, and what
about employing the third derivative?
I'm sorry, can you bring the microphone maybe a little bit closer?
I will try to.
I have troubles.
We can repeat it here.
Okay.
Question, what about using the third derivative?
Yes?
Intuition behind the third derivative.
So what the problem with the first derivative was? Or what?
Okay. In your paper, you explain the alternatives using a very rare pointing to some intuition behind that. And the question is, if we go to the third the order approximation or derivation, what could be the intuition behind that? That's the question.
That's a good question. I actually, I don't know. I have not worked with derivatives of that type yet, so I'm not sure. I'm not sure if it's computationally feasible to calculate that, and I haven't read about doing that in any of the papers. But yeah, basically, so if we say the second derivative is the curvature, the third derivative would probably be like the change of the curvature in this multidimensional network. And I mean, I assume that it could be used to even further approximate the function, and also to tune the weights and to remove weights, I guess. But I haven't seen that used in any networks, and I honestly don't know what the computational complexity and stuff like that would be for that. So I guess I cannot answer that question fully.
Okay, if there are no more other questions, we will go thank the speaker once again. And we will continue with the papers in this modeling session. So the first one is the poster and 2 more papers. Bye-bye, Paul, to Graz. Stay tuned for the rest of the CESCG. We have 1 more session to go, and then there's the awarding ceremony. And
I will. Thank you.
Bye-bye.
Bye.
Okay. Just go on. And I will turn it because we now like this.
Sorry, did you have like?
Okay. Now
It's not open.
sorry?
It's not open.
Isn't it? Okay, so then I will make oh. Okay, which one is it?
This one, just presentation.
This?
Above.
No. Good. And now we have like this. Right, and I just check here if it streams correctly. It does. Perfect. So there you go.
Okay, hi. So my name is Balázs. I was asked to be the chair of the next session. So the next session is called Modeling, and we have three speakers here. The first one is Gaja from Charles University. The second one will be Depner from Gaja University, and the third one will be Čavarga from Common University. So the first one is the paper with the poster you can see over there, and the name is an anisotropic reflection model for predictive rendering of FDM 3D printouts. And the speaker will be Anna. Please.
Hello, my name is Gaja. I study at University of Ljubljana, but currently I'm on my Erasmus at Charles University in Prague. I'm working on my master thesis, which is still a work in progress, and you can see my poster outside. I'm working with renderers and 3D prints, and our goal is to create an accurate rendering of a 3D printout, so with regards to the geometry and the correct reflections. So first a little bit about fused deposition modeling. So there are different types of 3D printers, and the one I'm working with is depositing molten thermoplastic material on top of the already partially constructed object. These layers then fuse together, and that is how we get our 3D prints. The instructions for the 3D printer are in the G-code, which looks kind of like that, and they're basically the instructions where the print head should move while extruding the material, the amount of the material it should extrude, and some other parameters. This G-code is generated by a slicer. So slicer is a software which receives as an input something as, let's say, a polygonal description of an object. Then it slices it into layers, and then these layers get represented as 2D polygonal paths, which the print head follows when extruding the material. And in this slicer software, we can also already get the previews of how our printed object will look like. But those previews are rather rudimental, and they serve more as a visualization. So we would like to make one that is a bit more accurate, so that it actually accounts for the geometry, how it will look like when it's printed. And it will have accurate reflections, which with regards to the filament material. This would allow us for virtual tweaking and virtual experimentation, and therefore we could cut down on the number of prints we have to make, because some of them don't come out the way we would like them to. So our first goal was to take the G-code from the slicer and then construct a model that will have accurate geometry, as you can see on the second picture. So it will actually have the tool paths, and then we also accounted for the subsurface scattering and the reflections, which give it its characteristic look. So it has some plastic reflections, and also you can see like it is partially translucent. That's why we get also subsurface scattering. So I will also pass this around, and you can play with them and look at them. So these are some of the renderings we created like this with cycles in Blender, and this PA I actually also have here, so you can judge how well we managed to match it to the picture. But yeah, as all of you probably know, things like that have a lot of polygons, and also subsurface scattering isn't the easiest thing to model, so it is very computationally expensive to make such a thing. So we, the biggest part of our master thesis is creating a shader which will try to match this without actually explicitly modeling it. So here we can see the pipeline. So we have a target model, which is like the models we usually use, and then we will try to create a shader which will have some sort of displacement shader, which will make this geometry like the you can see on 3D prints. and it will also have the characteristic reflections and subsurface scattering. We will try to measure the reflections so that for each light and camera angle we will know where the reflection should be, and hopefully this will look as similar as possible to the renderings we already did, which explicitly had the geometry and the subsurface scattering. And then we will also print the object, photograph it, try to match the light and camera pose, and then compare the three of them. And yeah, hopefully you won't be able to tell the difference. So that's it for me. Any questions?
I will start with one small question. You've been trying to reproduce the slices on the surface of the geometry, and the question is, you've been trying only to render the slices or to create the geometry of the slices?
Sorry, I don't understand.
Okay. First you've been trying to reproduce the slices on the surface of the model, and then to render it using the subsurface scattering. And concerning the slices, you've been trying only to render the slices or to create the geometry of the slices?
Well, for now we actually have the polygonal paths are kind of like a tube, and those are like 4 polygons each, and they're actually, as you can see, like the pictures.
Yeah. And
yeah.
The slices are there. They're only rendered, or the geometry created and then rendered?
It's the geometry. It's created. Yeah.
But what you're trying to do is to not create them, but have a shader that looks like this.
Yes.
But that's your future work.
Yes.
So what you have done so far is render this from the geometric description.
Yes.
And how are you planning to implement that? So is it going to be a local rendering shader or something in a full-blown renderer?
We're gonna use a Mitsuba renderer probably. Mitsuba renderer?
Oh, Mitsuba renderer. I see. Oh, yeah. Okay.
I have a question. I can notice that the bottom part is a little bit smoother because of how the heated plastic sits down, probably. Did you account for this in your simulations as well?
No, we're not accounting for like the physics yet, because also like you can see on the overhangs it's a bit different. Sometimes the overhangs are not printed as nice.
Yeah.
And things like that, but we did not account for that.
Okay.
It's a bit hard to model the physics. Yeah?
But like looking at the models, I noticed that the colors, the different colors have quite different properties. Like, for example, the silver one looked as more reflective. So will your shader account for the color of the material? And
Yeah, I mean we'll make measurements with certain materials, and then like those will be the options. Like we obviously can't make all of them, but I mean we will try to make more than one color.
We have time for one more question.
What are you planning for comparing the renders and the 3D models? So are you going to perform some user study or like some image-based method and image quality, or how are you planning to compare?
For the geometry we can actually make a 3D scan and then try to compare it like that. But for the reflectance, we'll probably just stick with the pictures, because user studies are quite hard to perform correctly, and it will probably like take longer than statistics to do it the way it should be done.
Okay, any more questions?
This is not a question. Would you be so kind as to stand at your poster and the other authors during the needed technical time we need after this session, so please be there, and if anybody has some more questions to these posters, use this time this way. It is a natural parallelization.
Okay. So, thank you very much. The second speaker will be Depner. The topic: improve integration of the images in 3D models.
Can I present it here in PowerPoint? It's actually F5. Okay, F5 and okay, and okay. So my name is Depner, and today I want to present you my work about improved integration of depth images in 3D models. First of all, I decided to show you an illustration of the workflow and possibilities you have. So imagine you have a depth sensor and you scan a room and you get depth images. What? Microphone, sorry. Okay, sorry, now everybody can hear me? Okay, so imagine you hold a depth sensor and you scan a room and obtain depth images, and that's on A, and on B you can see that you can reconstruct a surface using those depth images, and after that you can just apply some texture or do physical simulations like letting some yellow balls you can see on C falling down on the reconstructed surface, or on D and E you can see that also interactive applications are possible. For example, like dragging your hand and drawing on the reconstructed surface, or grabbing objects like this teapot here. You can tell on E that a person grabs the reconstructed teapot. Yeah, so next slide. Whoops. So why is my work important? 3D reconstruction is important because surface reconstruction has numerous areas of applications, like SLAM, for example, which stands for simultaneous localization and mapping. Their device scans an area, and it's also keeping track of that device within that area, and therefore a good 3D reconstruction is necessary. And what do we know? What I will also explain to you later is that Connect Fusion, which is the algorithm what I use for 3D reconstruction, only uses one depth image at a time to calculate the TSDF, which is the truncated signed distance field. It's an implicit representation of the reconstructed surface. And yeah, what our experiments are, we try to use previous depth images to calculate the TSDF, and our hypothesis is that reconstruction becomes more accurate and more reliable. Yes, and I think I'm holding it. So today's plan is to first show you the Connect Fusion pipeline, then talk about default integration, Connect Fusion, and then about our median integration. Then I will explain some meshing and implementation details, and after that we will look at some results. How does the Connect Fusion pipeline works? So first you make a surface measurement, so you get your depth image as input, and from the depth image is then projected into world space, and you get a vertex anomaly map. And in the first iteration of the algorithm you can jump right away to the integration. So you update your global, we call it global TSDF, which is the truncated signed distance field of all depth images, averaged, fused, yeah. And you can see also on 4, we have a voxel grid, and the voxels are here simplified as 2D squares, and for each voxel the shortest signed distance to the surface is assigned. And next step would be surface prediction. So we raycast the global TSDF, which gives us a new vertex anomaly map. And if we get now the next depth image for the next iteration, we have to do pose estimation. So we have to align the new surface measurement with our surface prediction to be able to properly do integration afterwards. And this is done with ICP. It's an algorithm which takes 2 point clouds and finds a transformation which aligns them like that you minimize the distance between the points of the both point clouds. Yeah. And that's the algorithm at all. And what we want to change is the integration. So how do we calculate a global TSDF for a voxel V? So first we take a voxel V and so we project its middle position onto the depth image plane and obtain a depth measurement, which you can see here is this orange dot. And the local TSDF is now only the truncated signed distance concerning only the current depth image we get as input. And the distance to this depth measurement can be calculated in camera space. So you transform the middle position of V into camera space, take the Z coordinate, and just take the difference to the depth measurement. That's shown here, the red line is now our local TSDF. And the local TSDF is just used in our global TSDF. We just take an average, we incrementally update the average. Yeah. And in the median integration, we now take also previous depth images into account. Here, for each depth image which comes as input, we first update the median vector of our voxels. So, for example, you can see here that there are some depth measurements inside this voxel, and they are aggregated or just calculated an average. And that's then the median vector, which you can see here, this big dot. And for calculating the local TSDF now, we just project again the middle position of the voxel V onto the depth image plane. We obtain a depth measurement, which you can see here. And now we take the median vector of this voxel, in which the depth measurement is falls inside. And then we just calculate the shortest distance to the median vector. It's actually wrong here, because it should be a line from one of these 4 vertices. Actually, I guess it is this one here, so it's that distance we take as the local TSDF. And then we also just use it in the global TSDF, and yeah, that's actually the difference. And meshing is either done with marching cubes on a default grid, or marching cubes for octrees. For the default grid, we just use Bourke's lookup table, so vertices are just separated by polygons, and for each inside-outside case, this is specified in the Bourke's lookup table. So we have, I guess, 256 cases in which vertices can be inside or outside of the surface, and yeah, we can see also here then the outside vertices and the inside vertices, and the resulting surface is the violet line. And marching cubes for octrees is a bit more difficult, because we have also different levels of voxels, so different sizes of voxels, and if you would just apply normal, so default marching cubes, there could appear cracks. Like you can see here on 7, this coarser voxel at the top with the edge F, and it's right next to smaller voxels which have different smaller edges, like here F1, F2, F3 and F4, and those edges does not match together, and there could appear a crack in the resulting mesh. And the idea is to replace the coarser edges with the smaller edges. Yeah, that's the idea, and the algorithm I used for that is okay. It's from Michael Kastan. It uses edge trees to do that. You can ask me later, I can try to explain it to you. And why should we use octrees? Because if we have maybe missing data in our voxel grid, like for example, here we have a vertex which has a missing truncated signed distance, we cannot mesh those voxels containing that vertex. And for the octree, we actually can do meshing for coarser voxels, and that can reduce noise and make less holes in the mesh. Yeah. And implementation was done in Infinitum v3 framework. It's an open source framework which already implements the whole Kinect Fusion pipeline in C++. And we modified it, or I modified it like that both integration types, default and median integration, run at the same time, and the exact same depth image data is provided during that. And the marching cubes for octrees is implemented by using the source code of the paper, which proposes the method for applying marching cubes for octrees. And yeah, let's look at evaluation and results. So I tested 3 different scenes, which you can see here. First scene is, it was in my own room. It's like a couch. The second scene is a flip table, because why not? And in the third scene, you can see some smaller, finer objects placed on the table. And we measured, to be honest, evaluation was not very good from my side, because we had no ground truth data to compare the accuracy of the newly generated meshes with the default generated meshes. So I decided to just measure difference between the mesh generated with default integration and default marching cubes versus different combinations of our median integration and marching cubes for octrees. What we can briefly describe here is that the median integration has its highest impact actually in scene 3 with a distance of 6.57 millimeters. So Hausdorff distance is just the distance between the meshes. And the marching cubes for octrees had actually the most impact on the meshes, which you can see the red and brown bars. Yeah. So I think pictures tell more. So let's look at scene 3. So you can see here the reconstructed mesh surface with default integration and default marching cubes. And this is now with median integration. The changes are very subtle. You can see some changes on the car, like on the engine cover. I think it's a bit more smoother than the original one. And you can also see that on the table there are less holes with the median integration. And there's another scene, scene 1 here, with default integration and default marching cubes. And this is now with only octree marching cubes and also using default integration. And you can see here on the left one, there are actually fewer holes, I guess. And here scene 2 again with default integration, default marching cubes, and now both median integration and octree marching cubes. You can see that around the edges of the table the holes get less, and also here, for example, here at this side there are fewer holes. And now this is actually, I really like that, because it turns out here to be very good. So this is the mesh with default integration and default marching cubes, and this is now the mesh with median integration and octree marching cubes. You can see that the holes on the table are reduced a lot. There are actually almost no holes at all, I guess. And also, if you look at the bottle, this little knob above is, in my opinion, better reconstructed than the original one. Yeah. What we have to do in future work is definitely do further evaluation, because we did not actually measure accuracy with ground truth data. We plan to do that with a framework called Blenzo. It's a framework which simulates depth images using ground truth 3D models. And we could also use additional metrics for mesh topology, for mesh topology, like mean or Gaussian curvature. And in my current work, I implemented change detection of 2 scenes the scenes are reconstructed using Kinect Fusion. And I hope that the median integration gives me a more reliable and accurate change detection. Yeah, that was my work. I hope everything was good to understand. Thank you for your attention and feel free to ask questions. Yes, please.
Yeah, so for your evaluation, you could actually 3D printing objects. Because then you have
Yeah.
precise 3D virtual model, but you also know its dimension in the real world, so...
Okay, I could try that, yeah. I was a bit lazy then later in evaluation. I could also do maybe like a sphere and manually do a depth image, but yeah, we decided it was enough for the evaluation. Like in my bachelor thesis, it was enough. Okay, yeah.
So I'm a little confused, like what the actual operation you use to aggregate the information from several depth images, because
Yes,
sometimes you like sometimes you like set mean, average, but you call it median.
Yeah.
So I'm not sure if you take the median or
mean,
the average, because for me it would make more sense to make like a average.
You mean that? Here just add all, so those depth measurements are 3D positions, and I add them together and just divide by the number of depth measurements which are inside. Yeah, that's just an average.
Why do you name it median? Because like median is a different operation.
Yeah, maybe that's my fault. Yeah.
That was very confusing.
Yeah.
So I would probably call it mean integration.
I'm sorry. Yeah. That's not a good. Yeah. Okay. Sorry.
And the second is not a question, but maybe a recommendation. Like during your qualitative evaluation, it may be a little hard to like see the difference between two images when you just switch them around.
Yeah.
Maybe do something like difference between the two pictures or some heat maps where the errors will be more obvious.
Okay.
Something similar to like yesterday we saw some differences between global illumination and the DDGI where guys made some like difference between the pictures or something. Because this is a little tricky to see.
Yeah, it's difficult to see. Yeah.
But there's just something to think about.
Perhaps another recommendation, you can also count the holes of the mesh by using the Euler characteristic, for example.
Okay. Yeah, I can try that in future. Yeah.
It's actually pretty simple.
That's a good idea as well.
So if you don't have a ground truth, how do you know the difference is actually an improvement?
Yeah, that's a really good question. It's actually just visually, it's very subjective, and I know it's not a good evaluation. Yeah. But I mean, yeah, that's.
You mean not median?
Yeah.
This evaluation is a standard problem of reconstruct real objects, because you don't have like ground truth objects when you're reconstructing some real scenes. So maybe this 3D printing is a good way to go.
Yeah, we actually try. We want to try it with Blenzer. With Blenzer, it could be possible to do a good evaluation.
So basically, this Blenzer is some framework for rendering some synthetic.
Yes, this Blenzer framework just takes a 3D model, computer generated, and it gives you depth image data of this 3D model.
Can it simulate the characteristics of a Kinect sensor or so?
I'm not sure. Because
it's rather
probably.
I think it's rather designed for laser scans.
Yeah, probably not. Yeah.
Maybe also you can like obtain some objects that have CAD models associated with them, like some machinery parts. You can like buy some set of machinery parts which have CAD models available for them, and then maybe scan those parts using the Kinect and compare it against the CAD models.
Okay.
or just use cardboard boxes with known flat sizes.
Yeah.
This is very simple.
Then you see a lot of work incoming.
Okay.
questions or more work for me to do?
I will quickly sweep all of these suggestions under the rug. Okay. And said, go to Stefan again.
Okay, thank you.
Third and last speaker is Čavarga from Community University Bratislava. Oh. And this topic is called Advection-Driven shrink wrapping of triangulated surfaces.
Hello. Okay, so let's sum things up with yet another modeling presentation. Welcome. I'm Martin from Comenius University, and after this presentation you will come to terms with a kind of special approach to processing polygonal meshes. So on the image you can see that we're basically wrapping a surface with another surface. Let me get my pointer. So our problem statement is to wrap some mesh, some triangulation, with a surface whose triangulation we can control. And we basically evolve it towards it and create something that looks like this. Now, why would we want to do that? Well, the type of evolution this is called the Lagrangian evolution, because we're evolving individual vertices. We're tracking a single surface rather than an entire field. But why would we want to do that? In reality, shrink wrapping is used, for example, to wrap the six-pack of your beer so that it holds together and there's more stability. And it's also useful to wrap other things, you know, like electronics. And then if we want to test whether the electronic, when it falls, whether it will sustain some damage, we can do finite element simulations. With this method, we can actually generate the mesh that is necessary for these simulations. We can also use this for filling holes, and eventually it may be used as a tool for remeshing, so improving the quality of the mesh. So we managed to actually, first of all, propagate the target mesh's shape into the surrounding space using a distance field. And then, of course, we needed to use its gradient as well to drive the sort of advection process that's inside. Our requirements were, of course, for the gradients to exist everywhere and to have reasonable computational time. We also managed to stabilize the model because of the numerical properties of it. Basically, the numerical method is unstable for certain sizes of triangular elements, when there's a lot of inhomogeneity between those elements, and we just use a simple scale-based heuristic to stabilize the evolution of a given input mesh. Now, to the SDF preprocessing step, we basically extract a so-called triangle soup, which is just a set of independent triangles, and we expand the bounding box of our target mesh into the surrounding space by an offset, generate a bounding volume hierarchy for fast searching through space, and then use this hierarchy to build an octree, which is only used to generate sort of uniform volume elements in space. It's basically, each node is subdivided whenever it intersects the mesh. And the intersection query is done using the AABB tree above. Now we need to create a grid where we define our distance field, of course with the given dimensions. And we set the exact distance values from octree leaf, cube of voxels, to the closest triangle. So we basically transform it to the index space of the grid and set infinity everywhere else. And this serves as an initial condition for the so-called fast sweeping algorithm, which basically sweeps across the entire grid 8 times and finishes the rest of the field. I mean, optional, we can compute the sign of the distance field using a flood fill algorithm, much like the paint bucket tool in MS Paint. Now, the mathematical model itself consists of, well, basically this nonlinear differential equation. On the on the left-hand side, you can see the velocity of the surface, and here you have the curvature term, where without the epsilon, it would be just mean curvature flow, so it would smooth out all the features and sort of shrink the surface into a sphere. The other term is the advection part, so that's basically leading the surface along a certain field. And then there's tangential movement, so that we don't have accumulating vertices in one spot. Now, the control functions that we used are pretty similar in the first and the third term. There's just a little inverted exponential sort of Gaussian. And the eta function actually also contains the dot product between the negative gradient of distance and the normal, the unit normal to the surface. So what it basically does is that it rotates the surface so that these two vectors align. Now, the types of tangential redistribution that we use are angle-based and volume-based. The first one is just homogenizing angles of adjacent triangles for each vertex, and the other one homogenizes little volume elements, sort of neighborhoods around each vertex that I will refer to later. The angle-based is the best one for us at this point. Now, to understand a little bit what the eta term does, here's a simulation on a test mesh. Without the square root term, with the constant d, it just produces a membrane that stretches over non-convex parts, and with basically that's a sine part, it fills the non-convex region, so it goes inside the cavities. Now, we have to do a numerical analysis of our problem, so we just transform our smooth model into the setup with our initial surface, which is a triangle mesh. So we combine it and integrate over these little volume elements, or two-dimensional volume elements actually, that surround each vertex and basically cover the entire mesh. They will be referred to as covolumes. Now, we also discretize the Laplacian that's used in there for the curvature term, and we do that using a cotangent scheme, first introduced by Meyer and colleagues. Now, we put all that into a system of linear equations that has a diagonally dominant matrix. So all the terms that refer to the curvature are stored in the matrix, and the rest that refers to the previous time step is in the right-hand side. And we solve it using a custom-made BiCG stab solver, the stabilized biconjugate gradient method for large linear systems. So by actually wanting to stabilize the model, we consider the requirements for the semi-implicit approach to actually be stable. So the simple heuristic is that the time step should be approximately equal to the square of the spatial step. So in our case, it would be approximately equal to the average measure of the covolume. So we adjust the scale of the evolving surface so that this condition is satisfied. Now we start with an icosahedral sphere with some subdivision level S and radius R, and basically this is what it looks like. And because the icosahedron approximates the sphere, we assume that the distribution of vertices is more or less homogeneous, so we just divide the number of, I can see that on the screen, we just divide the surface area of the sphere by the number of vertices, and that's how we get our scaling parameter phi. Now the question is, how many vertices does a recursively subdivided icosahedron have with subdivision level S? to answer that, we start with the basic number of vertices and edges for an icosahedron, which is 12 vertices and 30 edges. And then we solve this system of recurrence relations for the number of vertices. Now, basically we interpolate between two different values of the scaling parameter to achieve satisfactory results. Now, we tested the performance of the SDF algorithm for 6 different meshes. You can see that a lot of them, well, the most interesting thing is that the AABB tree construction is independent, of course, of the voxel size, of the voxel resolution. And we also did that for 3 different CPUs, as you can see. And we notice that in the table, the first part actually refers to processors with roughly the same clock speed. And the other one is Intel i5, which is approximately 1.5 times slower. Now, we also have 2 different setups, intrin and no intrin, and that refers to using C++ intrinsics or advanced vector extensions used for computing the optimal split position for construction of the AABB tree. Now, we also simulated the stability of our meshes. So we start with our test meshes, and we do that for different time steps and different scaling parameter values, phi. And we can see that we're able to stabilize the mesh, for example, by using a relaxation function for the tangential redistribution, the rho, in the second column. And also, well, basically, the graph shows how many time step the evolution survives without collapsing. And we can see that when we're in that sort of region that's given by the heuristic with the boundaries from maximum and minimum scaling parameter values, we're basically safe. And we also measured how close to the target surface is the actual resulting surface. So that's the distance to gamma. And we also did matrix for finite element analysis. For example, minimum internal angle per face, maximum angle, and the condition number of Jacobian between unit triangle and the transformed triangle. So you can see that triangles that are really stretched have high values. Now this is what it looks like for other meshes for different subdivision levels. This is the distance evaluation. This is the minimum angle, maximum angle, and the Jacobian condition number. Now, there are other approaches similar to this, of course. The first one was done by Kobelt and colleagues, where he basically did a form of remeshing and corrected for the distorted deformed parts. Also, a similar approach was used for extracting brain images in tomography, and it's widely used in brain tomography as well. And then there's an article from Zacht and colleagues that basically creates a hierarchy of nested cages around a target mesh. So what's next for us? We want to refine the triangles during evolution so that we adjust for the stretched triangles, doing topology adjustments to mesh. We also want to do a little more better design of our experiments for stability simulations, optimize the ABB tree construction so that it's even faster, try evolving marching cubes isosurfaces, and also extend our method to quad meshes. So that will be pretty much it, and I'm ready for your questions.
Maybe I will start with the first question. What changes will we need for the extension for quad meshes?
There's a method used by Medla and colleagues from the Faculty of Civil Engineering, which basically does the same thing for quad meshes. So the operator, the Laplace operator, can be extended to quad meshes. Basically, the co-volumes look the same. They go into the centroids of the quad, and basically the operator works in very similar way. So it's not that difficult to extend it.
Okay. Could you use this for UV parametrization? Like the sphere has a UV parametrization that is easy, and then you shrink wrap it onto the object?
Yes. The article with Cobalt in the other methods actually uses a similar approach. So you can see that the bunny above is actually made from patching up together different patches with some distortion. So that's how Cobalt and colleagues did it in 1999. So a very similar approach.
Okay, and then I would have another one. So you mentioned refining triangles during the evolution, and what would you use to determine where to do that?
Matrix, like for example, some difference between principal curvatures, where there's a lot of stretching, for example. But you can essentially do, well, you can weigh the probability that you want to flip a triangle or split an edge or something like that when you need it. So you basically have a scalar function on top of the mesh based on requirements that you need. So
do you think it would be possible to use some kind of global geometric operation instead of local ones? So not just flips and...
Well, the simplest global operation is to split long edges. So you have a threshold, but I don't want the edges to be longer than 2 centimeters. So you just split those that are longer.
Yeah, well, what I'm thinking about is to identify an edge loop, especially with quad meshes, an edge loop or a face loop, and then extrude, split that loop in one step.
Yeah, it's possible, but it would require, like the topological operations are complicated in the fact that, you know, basically you can affect the results along the way. For example, if you do splitting, you know, you can also make your geometry worse. So this is something that requires further analysis, of course.
So let's have a speaker again.
So a few organizational remarks. Now there is the voting. So please cast your votes very quickly. We need to count them. In the meanwhile, there is the poster session. So I would like actually to ask the authors of the posters to stand close to their posters if you want to discuss with them. You already heard all the presentations, so you can still have more questions and stuff.
Okay.
In the meanwhile, we count the votes. We prepare the awards, and then there is the awarding ceremony. Afterwards, there is lunchtime. Before you leave, I have one question. Approximately, how many of you are going for the procedural workshop, and how many of you are going for the WebGL/FEM workshop? So let's vote for who is going for the procedural one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I have a question regarding that.
Yeah.
Because we were supposed to write our preferences. But is my preference meaning that I'm actually going to that one?
No. The preference is just a preference so that we can assemble the schedule so that it fits the most people. No, now I was asking, did you already decide? And those who decided, where are you going? And if you didn't decide, you will decide in the next 2 hours.
But it's not up to my decision. Just said, like, it's just a preference. So I have a preference.
You can decide. The preference is just for planning, approximate planning.
You will just attend.
You can decide now. You are being asked where you will go.
You can decide anytime, you can switch the workshops, whatever.
So there's no limit, like there could be only 10.
No, there is not. I just wanted to know where the workshop should happen, just to know if I have at one workshop 20 people or 5 or 4, just because of the room allocation. Otherwise, everything is up to you to decide.
I also have a question about this. If you have this, like the procedural stuff has like 3 time slots, is it all 3 time slots?
Yes, basically it's thought to be meant to be like that.
Okay.
If you wish to switch to finite element methods, it's no problem.
Ja by som chcela voting sheet.
Musíš sa spýtať Diany a Annaleny, či máme spare. Ale skôr nie. How many did I count? 12? Which would mean that for you it's then less. Would you like to have it indoors or outdoors?
Indoors is fine for me.
Okay.
You have more of this?
For people who lost them, which is unfortunate because I don't think so that there is Annalena and Lucas discussing the same issue right now.
And here we can thank Martin, our hero, who made everything possible, as you can see. Martin, a big hand. Yes. We can thank our live viewers on YouTube for watching here. Maybe let's give them a hand. Yeah.
There are none.
Okay, then we use this applause for our sponsors. You don't need to clap again. So this is again for our sponsors. There are several of them, especially the Kaust and VRBIS. I would mention them. They have very large contributions to the financial survival of this event, which is not always easy, because as you can imagine, all of these things cost money, and to keep the fees low, I mean, there's so I think the fees are currently lower than what each additional participant is in cost, so we need additional income from the sponsors. Yeah, in the IPC meeting yesterday we discussed several options how to continue to have this, but I think we found things. Yes. So, how are we with the documents?
So I didn't make everything possible. Thank you. I didn't make everything possible because the documents are not printed.
Oh, okay.
Because there is an issue with the template, and we can't print it. Right now it's stuck at Inkscape exporting it into PNG, because if you export it to PDF, it's wrong. So our suggestion with Lucas would be to have lunch and do the awarding afterwards, or we can decide right now that we do it without the printed stuff.
I think we do it without.
Okay, maybe
everybody's waiting already.
Maybe I can try from that hard disk to screen it over here.
Yeah, that's good.
But I'm not sure if I do have the last version saved, so I will check.
You mean the names of the
I mean the names,
might
of
be
course.
different.
Maybe you see the names from previous years.
Exactly, so let's try that.
Let's try that.
Okay, Martin will try some wizardry here, and we'll see. So to remind you, we have a couple of awards. So there's an award for the best video, and there's an award for the best poster. In each of these two cases, the decision was very difficult. So we had 2 video presentations and 2 poster presentations. So it was a very hard choice among the many options. And then you voted on the best presentation award, and the IPC decided, mainly based on the reviews that were handed in by the reviewers, on the best paper. I have to say that the best paper was a really difficult decision. Actually, the papers, and from what we got from the presentations, really there's so many really good papers. So I have to say that now the selection is these are just selecting 3 based on a very minor epsilon that maybe came out mostly in the review process, but actually the list of candidates that had like scores that were really in the very high range was like a long list. So it's kind of almost 80% of the papers as well. So it was so even if you will not appear now on this list of awards, consider yourself awarded with the honor of having presented together with all the other presenters here, and having performed your first presentation in front of this international audience. And I think this is an award in itself. And I think you all deserve it. You all did great. And yeah, I think we're getting close. While Martin is writing down the names.
This looks good. This looks good as well.
Verifying.
This is not.
No, this is not.
This is not. Okay. This is not.
Still checking.
So I think I need to fix it right now.
Okay, so Martin is fixing
does
it.
anyone have the booklet, please? I could borrow. Yeah. Just to have the full program.
This is yours anyways.
Man. You're right.
So we had many, Czech in the history there was there are so diverse social programs. I think one, I didn't, in the opening speech I didn't explain some of these images. Maybe you remember there's an image of this of a car with about, I don't know how many, but 15 people. So I think it was how many people you can put into a Lada. Car. What? Skoda, yeah, Skoda, I'm sorry, Skoda car, yeah, a Czech car. There were really a huge number of people, so yeah. And that's what we tried many years ago.
Has there been an attempt on like upping the record or?
Not since then. This image was mainly used as illustration or as motivation for similar endeavors. Yeah, exactly. Yeah.
It was after the pub session.
Yeah, exactly. Yeah, maybe the problem was getting from the pub back to Budmeritzer Castle, and it is a walk. I think it's a 15-minute walk or so. And after the pub session, people were not so motivated anymore, and maybe also not capable of walking in straight lines.
But the truth is that the car was not able to move anyway. It was just standing on the street, like flat tires. Now.
Before or afterwards?
Before already.
Okay. Don't spoil the story.
So next time bring your broken Skodas.
Tell more jokes.
Okay, so I will now randomly select some people to tell jokes. Yeah. Szőke, do you have one? No, it's not a good joke. Yes. Okay, let's see if
Just from an exam on image processing, and there was a question that explained how the Fourier transform work for the images, and there was an answer that the Fourier transform changed the images in the way they are not same anymore. It's better in Slovak, I really can't really translate it. But yeah, now it's your turn again.
No, let's now. Next one, please.
I actually know one on Fourier transform. So, do you know what an Egyptian cat looks like? It's like really bold. And so, how do you turn an Egyptian cat into a Siamese cat? Using Fourier transform.
Do we have any more jokes on Fourier transform? Somebody could make one up. Okay, so any other jokes not on Fourier transform? But hopefully Martin is very soon.
I have no Slovak keyboard here, so I'm sorry I can't write down the diacritics.
No hot checks and no accents.
Just approximate the names, it's okay. Save time.
But Lucas told me on phone in the meanwhile that he managed to circumvent the problem by using Firefox instead of Inkscape. So maybe he will run in here with the diplomas already. Let's see.
We will start anyway, and then we can redistribute the
exactly.
Yeah, so maybe I can tell about some other experiences at the Budmeritzer Castle. So Budmeritzer Castle was maybe not in. It was built maybe in a bit lighter way, one could say. So there was the main lecture hall. That's a bit similar to here. But there was no way to darken the place, so we usually put up some aluminium foil on the windows and glued them there. And also there was the special thing that there was a big room for apartment up directly above this hall, and usually it housed like 6 or 7 students. And it ever so happened that some of these students well, they had longer nights, I would say, and they did not make it to the first session. And then somewhere during the second session, you could feel or you could hear and notice there was a big kind of chandelier, so hanging from the wall, and you could notice when they started to get up and started to walk around, so you really it was crunching on top of the lecture hall. This was quite interesting to notice how some people have spent the night.
We are good to go.
We are good to go. Okay, very good. So I think I did enough thanks already. So we will, without much further ado, we will start with what award? Best
Just a
video?
second. I just set the screen. This says closing ceremony 2021. I didn't update the logo. Sorry. Yeah, I think we start with a best video, perhaps. Yes, exactly. We start with best video. So
okay, the best video. As I said, we had 2 submissions.
there are 2 types of awards donated by the audience. That is the best poster and best presentation. And actually, yeah, I don't have the poster here. I forgot about it. So we have to catch up on that. And 2 types of awards awarded by the jury. That is the best video, best scientific video, and the best paper award.
I think I mentioned this already.
You did, sorry. Okay. And I have one more announcement to make. Thank you. So this year we have the prizes donated by Escape Motions, which is a small design company from Piešťany, Slovakia. They do great software for creative artists where you can paint and create fractals and stuff like this. So all awarded students will be able to choose one license for one type of software from their house. If it happens that you get 2 prizes, 2 awards, then you can select, of course, 2 licenses, 2 different licenses, okay?
3 years.
And I think that's not the case. And the second thing, and this is the most important announcement, is that Capturing Reality was a Slovak company that developed a software called Reality Capture for 3D reconstruction. It is the fastest 3D reconstruction software in the world. Last year they were acquired by Epic Games, and now the software gets its way into Quixel and into the Unreal Engine slowly. We are right now negotiating with them. Once the contract is signed, I will have a promotional key for, I think, almost each of you. And the awarded students will get then these super big licenses, perpetual, I think, not sure, from them. Here it doesn't apply. If you get 2 prizes, you get just 1 license. And I still can't confirm this. This is like 95% it will happen, but we need to close the deal that we didn't make before the CESCG, because now being corporate, it's a bit more difficult with them to get licenses. They are very keen to give them away, but it needs some legal background. Okay, that's what I wanted to say about the announcement. For you, it means that most likely all of you will have the chance to try out their software for free.
Okay, you're now wondering, will I get an award? Will I not get an award? So let's ease the pressure and let's solve this riddle. So who is getting the award? So for the best scientific video we have Martin Čavarga from Comenius University about advection. I can't even pronounce this, it's so complicated. Come here. Advection-driven shrink wrapping of triangulated surfaces. Congratulations!
Awesome.
Yeah, and now I hand you a virtual sheet of award. Okay, so congratulations again, and we provide some pixels. Or yes, pixels. Here. Okay, very good. Okay, perfect. So this is the best video award. Do you want to start the video?
Actually, we can. Let's say on the end,
yeah,
on the end
yeah,
of the session.
We'll show this at the end. Yeah. Okay. Next is the Yeah, there's actually 3 best
Is it?
presentation awards. And
Scientific. Yeah. Okay. That's right. That's right.
so the 3rd best presentation award goes to Maroš Kollár from Slovak University of Technology. Congratulations. The paper is multiclass texture synthesis using, you're taking away.
Sorry.
Using generative adversarial networks. So, congratulations again. Here are the pixels. And here is your virtual certificate. The 2nd best presentation award. Martin, what are you choking?
I am always on the live stream. For the no one on live stream, I am switching it because still it gets recorded.
Okay. The 2nd best presentation award goes to. We have seen this name already. Čavarga from Comenius. He is a student of Andres.
Put it here.
Okay. And again, pixels. Okay, and now for the best presentation award. The best presentation award voted by you, the audience, goes to Wojtek Thomas. The best presentation on the piano and also the best presentation in the conference about urban data visualization. So here you have the virtual certificate and let's provide pixels again. So, I guess we should have the best poster now.
No, we don't have the poster in the slides. I'm sorry.
Okay.
But you remember it, right?
Yeah, the best poster. What?
The TV is sleeping.
The TV is sleeping. It got bored.
Uh-huh.
You have to tell better jokes.
How is that possible?
So, if I remember correctly, the best poster award goes to our Anna, Gaja, Boss. Yeah. Congratulations. Your certificate. You can stick it onto your poster. And now for the best paper awards.
Oh, good timing.
The 3rd best paper award goes to.
Aha. Tu je tato. Sorry, what are we now?
Best paper.
Best paper already? 3rd best paper.
Yeah, Dominik Bořek. So, wait, you get your virtual certificate.
No,
so
you get the right certificate.
It's already existing.
You get
Możesz, daj.
this one.
Thank you.
So, again, pixels.
Thank you.
Congratulations. So now we are moving to the 2nd best paper award. And that is also this name we have seen before, Wojtek Thomas. Congratulations and pixels. And finally, the best paper award.
Sorry, wrong button.
Yeah. The best paper award, and I have to say this is really about the paper, so the presentation you voted yourself. sometimes the presentations have unforeseen problems, but the paper was really based on the written presentation. And here, this was extremely convincing for everybody, for all the reviewers and for us. And we are happy to announce that the Best Paper Award goes to Paul Eibensteiner. now we switched. Now we have a real certificate going to a virtual participant. And we provide some pixels. Hello, Paul. Okay. And yes, so then there's a few, I think I mentioned this already before, so our heroes of CESCG, would also like to mention also Anna-Lena, who helped with the registration and many other aspects. Diana we heard already, also with the registration, and Max, our secretary in Vienna. I also want to thank myself for telling bad jokes. And also the TU Graz team, which hasn't been mentioned enough maybe, who handled the scientific organization process. So Markus Steinberger, Pascal Stadelbauer, Daniel Mlaka and Alexander Weinrauch. They helped us a lot with with handling the scientific program. And from STU and Bratislava and from Comenius we have Lukas here. Thank you. We can actually give him Miroslav Lazzo and Stanislav Grigor. So Stanislav is here doing the video recordings. And of course, I already mentioned the father of CESCG, the mother of CESCG, and the uncle of CESCG. You have heard that. So let's thank Andre again for giving us this beautiful event, and also the others. Again, thank you. Yes.
I have to clarify again. It's Helvig. Helvig is the father and mother. And I just had a single, so to say, footnote that the event in Slovakia will be cheaper. But what are the Austrians doing with some minor inputs? Maybe you know the Meister Eddie Greller?
Yeah, this is not so well. Meister! Yes, this is not so well known among the younglings, so we have to.
Helwighauser and the other guys invented that in the early morning they will greet their master, and they were searching for some gestural interface. And he was very excited, Eddie Greller, by bifurcation. So he showed this many times in his lectures. So they entered their...
Yeah, exactly. The funnel. This is the universal symbol for the Meister. It's the funnel, and the big funnel is like this.
After big funnel and the kneeling and
kneeling and so on.
And people around Karlsplatz, Vienna. This is the Miesto Činu. This is the crime scene where this happened. The people around were observing what the academic people are doing, and they recognized that one person is needed to be greeted this way. And when there was more space, huge groups of people were doing this, and his wife didn't have any guess, any single guess what's doing around Eddie Greller. And one day there was the Opernball or something like that, and in the foyer of Vienna Opera a group of people did this in the shocked face of Eddie's wife and himself. It is a religion. It is a religion with no message. And Eddie Greller was always explaining that he is not the master, but they hacked his website. They gave him this aura. They sent everywhere the Meister Edigrelo. It was copied by thousands of secretaries worldwide. And Meister Edigrelo is something like in Czech culture Zimmermann. Which is a fictitious entity, and this just was, yes, I thought it will be cheaper. When Helvig was classified as mother, this made some mismatch in imagination of our lives, our real lives. So, well, Alan saved Czech alive for several years, really. Now, Helvig did everything, but Helvig is a representative of excellent team by Werner Pulgadhofer, Faurelis, Graz, where I had the chance to serve for 3 academic years, and so on. And this was the wonderful network of teachers and students, and this would be not possible without computer graphics discovery. And this is the time for goodbye saying, and I have another piece of liquid animation for you. But see you later.
Thank you, Andre. So while we may provide our pixels, Andre has kept Czech alive also by providing sound waves at different events, so this is really beautiful. So I think this concludes the award ceremony. Congratulations again to all the winners. Maybe a final big hand. Is anybody hungry, by the way? So there might be lunch being served afterwards, and then we will start and have fun with the academy as well.
We forgot one
important thing.
And that is that Daniel Corner from VRIS was supposed to come, but he couldn't because he, long story short, a colleague of him in the office got tested positive, so Daniel decided that he may be positive as well. He didn't want it to be dangerous for us, so he stayed in Vienna. This means he should have bought 2 more goodie bags, because the IEEE section Austria always donates awards and goodies for women in computer graphics. So this means that Sania and Michaela, who had papers at the Czech, will get goodie bags. We just need their basically. Michaela is at Faurelis, so that's no problem. But we need the address from Sania so that we know where to send it. And yeah, so this is the last kind of award or goodie thing for today for the awards. Please, ladies, stay true to visual computing.
Now I can only say Stachnik. For whoever understands this, no? Yeah, some understand, yeah. For the who doesn't understand this, you can ask Andre about it, and for the others it's Mahlzeit.
Dobre. This also concludes our live stream. If anyone is watching